Today, we will look at the structure of the nucleus in the sense that we have been talking about the nucleus and then later on to the nucleons and the protons and neutrons. Further, we went on to the substructure of the protons and neutrons and then discussed the Quark model, which tells us that it is possible to consider quark as the basic constituents of all matter along with the electrons, of course, and especially considering the nucleus. Nucleus is made of quarks, and these quarks can form bound states, or they are found only in bound states for that matter. No free quarks are found, and quarks can be formed in two different different types of bound states. One is basically consists of 3 quarks, which are called baryons like protons and neutrons. And then we also said there are particles which are non-baryonic, which means that is slightly different from the protons and neutrons, etc. They are made of quarks and antiquarks, one quark and one antiquark, and they are called mesons. Examples are pions, kaons, etc. So, we had all these theoretical description, and we had a consistent picture, and we introduced ourselves to this notion of quarks. How do we actually test our ideas experimentally? At some earlier stage, we had in fact mentioned that it is basically the scattering experiments that gives us information about the structure of the nucleus and structure of the subnuclear particles and even particles inside the nucleons, which are quarks. And we also said that the scattering experiment is basically the kind of experiment that Rutherford and his collaborators had performed, giving us the information about a hard nucleus consisting of all the positive charges in an atom. So, we have to, in understanding the substructure, the quark level picture of the protons or other hadrons, we have to rely on again scattering experiments. Okay. So, first we will spend a little time discussing the structure of the nucleus, or how do we actually come out with the interpretation that the nucleus itself, I mean going beyond Rutherford's experiment, say that there are actually substructures in the nucleus like protons and neutrons. Okay. So, let us look at this. The Rutherford's, let me just remind you what the Rutherford experiment cross section is. So, let us consider Rutherford scattering. Now, let us consider electron scattering on the nucleus rather than alpha particles, just for somewhat giving a little simpler picture. So, we define what is called the scattering cross section. Let me call in this particular case this Rutherford scattering cross section d sigma over d omega, which is related to the number of particles that you will observe at an angle theta in a solid angle d omega. This is basically in the case of electron nucleus with a Z number, the atomic number Z, we have Z e square whole square 4 pi epsilon 0 square 1 over 4 kinetic energy of the electron square sin 4 theta by 2, and theta is essentially the scattering angle. So, if you have a nucleus and electron sent towards this one, it will see the electrostatic potential, okay, and scatter at an angle theta. So, this is the theta angle, and corresponding cross section is given by this. And solid angle, just to remind you in case some of you do not have forgotten what is a solid angle, it is basically sin square theta d theta d phi in polar coordinates, okay, or it is basically the area of a cap of radius r divided by r square. Now, let us have some theoretical understanding of this whole thing. Basically, let us consider the initial electron wave function as okay, the wave function is psi I, let me denote it by that, and then final electron wave function after the scattering, let me denote it by psi f, okay. And between these two, the electron undergoes an interaction. So, interaction of the electron with nucleus, let me denote that by a Hamiltonian part H interaction. So, interaction Hamiltonian, the potential essentially, okay. In quantum mechanics, the corresponding operator. So, we can say that the probability amplitude for an electron in psi I wave state to interact with H interaction to transform to state psi f is, let me denote that by T f I initial to final, is basically H I n t sandwiched between H I and H f. This is the quantum mechanical probability amplitude for this particular thing to happen, and the corresponding probability itself okay, for, let me write that down, for psi I to go to psi f through H interaction is equal to now T f I square. So, this is basically the quantum mechanically schematic way of writing the transition of the electron state when it scatters of a nucleus or encounters any such nuclear potentials or any such potential in fact. Now, usually in an experiment you do not have a particular electron which is sent on a particular nucleon. Rather, you will have a beam of electrons like a beam of alpha particles sent to a target system of a target nuclei, many such things like alpha particles sent to a gold foil. So, let us connect with experiment like this. Where we have a beam sent to a target and then we observe these scattered particles. Okay. So, in that case what is detected, number of particles which are scattered into certain areas, or you go over around the whole of the target and then get the all of the target scattered particles. Or if you keep a detector at some particular angle, it will detect the particles scattering into that angle. Okay. So, we can now think about reaction rate, which means the scattering rate. So, per target particle per beam particle. Okay. Let me denote that by what is called a letter W. Okay. E is equal to T F I square, the probability, into what is called the number of or density of final state which is available, and 2 pi over h cross. This is an expression which can be actually derived considering the quantum mechanical process of scattering. We will not go into the details of how to get this, because that will take us away from our discussion. Rather, I will point you to where you can read this and understand it if you are not already familiar with this. You can take any book on quantum mechanics to understand this. Usually there is a discussion on scattering in any basic quantum mechanics book. Specifically, if you can look at the quantum mechanics by the classical book by Schiff. Okay. So, here rho is basically the number density, number of states, density of final states, okay, that this beam can go into, number of available states, density of final states between energy E and E plus d. Okay. So, with the TFI described in the earlier slides, we can write now W as 2 pi over h cross, 2 pi over h cross psi f h interacting psi I square dn by d, which is basically E, rho E. Okay. Fine. Now, we will see what is this number of final state that we are talking about. Let us consider a particular particle, and what is the minimum space that it will occupy in its phase space. When I say phase space, it is the space spanned by coordinates, position coordinates, let us say, or the position coordinates and momentum of momentum. So, it is a 3 dimension for the coordinates and 3 dimension for the momentum, together 6 dimensional space. Okay, 6 dimensional. Idea in why we are talking about phase space is because essentially when we talk about a particle, the kinematics of the particle, what we need to know is where the particle is and what the energy of that particle or the momentum of that particle is. This is what basically we do when we say that, okay, go back to the Newtonian mechanics, classical mechanics or any such a thing. there also, when we say that we understand what the dynamics is, basically to understand where the particle is and how it is actually traversing in space and with what momenta at any time. Okay. So, therefore, the phase space is one of the important things to know. So, if you know where the position, what the position of the particle, position meaning where the particle is in the momentum and coordinate space together, which is called the phase space, then we know what its kinematic, what its energy is, what its position is, etc. Okay. So, that is what, and the trace of this will give you the evolution of the particle and then give a lot of information about the dynamics again. Now, let us consider a particle. In quantum mechanics, a particle's momentum can be determined with some minimum uncertainty. Okay. You cannot go on to determine the position to finite, very infinite accuracy. And the uncertainty principle tells us what is the accuracy with which we can actually go. So, it is essentially that delta p, the uncertainty in the momentum, times the delta x, the uncertainty in the position for any particle, is of the order of h minimum. So, that is the minimum space needed for a particle if we consider a one dimensional system. And in 3 dimension, it becomes 3 such coordinates and 3 such momentum components. So, the phase space volume per particle or needed for a particle is about h cube in 6 dimensional phase space. Now, consider a particle scattered into a volume, spatial volume V, and has momentum between p and p plus dp, and this will tell you the phase space available in this particular case is equal to V times 4 pi p square dp. 4 pi p square dp is the volume in the momentum space for momentum between p and p plus dp. That is only the magnitude that we are considering. So, we have to integrate over the spatial angles, and then that will give you a 4 pi factor, 4 pi p square factor. Okay. So, this is the volume phase space available for available total. So, per particle or the number of final state particles or number of final state available for which means how many particles can be accommodated in this volume is what we are considering. dN is basically available phase space divided by the phase space volume occupied by one particle, which is h cube. So, we can actually write it in terms of energy by considering the fact that P is equal to E by C, relativistic relation, So, that will give you dN equal to 4 pi E square, P square becomes E square by C square. So, we will take into account what the thing is, C, the factor of C will come down. dP is dE divided by C. So, there are 3 C factors, CH cube into V, or I can write dN over dE, which is what we considered as rho earlier, which is basically the number density between energy E and E plus dE is equal to 4 pi E square. Let me write H in terms of H cross, which is 2 pi H cross C cube into volume, special volume. Keep that in mind. We will take that information at a later stage. Okay. Right. So, we will now connect this with the cross section. So, what is this? Let us consider again the rate of reaction rate into solid angle d omega per target particle per beam particle. Okay. This is basically W, but not the whole thing, only into solid angle d omega. So, what we mean here is, what is the rate of reaction if there is only one particle coming in, okay, into a solid angle d omega, okay, and at angle say theta whatever. So, now if number of particle in a beam, if this is equal to n b and number of particle in target is equal to n t. When I say number of particles in the target, it is in the within the cross sectional area of the beam, which is what is relevant. So, basically the region here, okay. So, the region here, all through that thing. If this is labeled like in that fashion, we can say that rate of reaction or reaction rate into solid angle, in this case with Nb particles in the beam and Nt particles in the target, is W Nb Nt d omega. Okay. And which means that if you have such a reaction, such a scattering experiment where there are Nb particles in the beam and Nt particles in the target, then scattering into the number of particles that is going to scatter into the solid angle d omega per the rate of this particle, okay, the particle which is going to get into this thing per unit time is basically W d omega, which is essentially the reaction rate per target particle per beam particles. So, you have to multiply it with the number of particles in the beam times number of particles in the target to get the actual reaction rate. Now, let us connect it with the cross section. For that, we had already discussed earlier what the cross section is, etc. in the when we discuss the Rutherford experiment. So, let me remind you what we had there. If you have a nucleus like this, or take a hard sphere scattering, which was what we considered as an elementary scattering experiment. So, if the particle in a small cross section scatters into a solid angle d omega at an angle theta with the beam direction, then the d sigma, which is the cross section of the beam, relevant portion of the beam, times the flux of the beam, number of particles crossing cross section area in unit time, per unit time and per unit area of the beam cross section, times the number of target particle is going to be the number of particles scattered into solid angle omega, scatter angle, solid angle d omega. Flux itself, flux can be written as number density into the speed. All right. So, that will give you the volume number density. Nb is the number of particles divided by volume into Vb is basically the speed. Of the particle. Okay. And so, this Nb is what we had defined earlier. Okay. So, this now tells you that d sigma flux Nb by V into Vb into Nt is equal to number of particles scattering into solid angle d omega, which is W d omega Nb Nt, or you can write d sigma over d omega equal to W V by Vb. Now, go to slides 3 and 4 to get W, and write it as, write then d sigma over d omega as 2 pi over h cross, there is this that is W into psi f h interacting psi f square dn over de into V by Vb, and dn by de was given in slide 4. So, and let us approximate Vb to C. So, that will give you V over C 2 pi over h cross psi f h interaction Hamiltonian this should be psi I square 4 pi e square dn by de is 4 pi e square 2 pi h cross c power 3 into V, and the whole thing then becomes V square e square 2 pi square h cross c power 4 and factor of 4 pi psi, which we will worry about later, h interaction psi I square. Okay. So, this is your d sigma over d omega, what we call the differential cross section. unless we know what H interaction is, we will not be able to proceed. So, let us look at the case of electrostatic interaction. Electrostatic interaction between the electron and the nucleus. See. In that case, interaction Hamiltonian is E times the electrostatic potential, and in quantum mechanics it is the corresponding operator phi. And we can write psi I as 1 over root V exponential I p dot x over h cross, and psi f, the wave function in the final state, as exponential I p prime. Let us say the momentum is denoted by p prime in the final state, and that will give you psi f h interaction psi I equal to E over, there are 2 under root V's in the denominator, will give you 1 over V, and the transition matrix element in the coordinate representation is exponential I p minus p prime dot x over h cross phi x d 3 x, or I can write this as E over V integral e power I q dot x over h cross phi of x d 3 x, where q is the momentum transfer, change in the momentum. Okay. Now, we have to understand what this or phi is, or we will actually do some algebraic manipulation to get it in a better form. Okay. Let us consider the del square operator acting on e power I q dot x over h cross. This will give you minus q square, minus because of the I there in the exponent, over h cross square, then so the same I exponential I q dot x over h cross. This then what we can do is to write e power I q dot x over h cross as h cross over q square with a minus sign times del square acting on the same operator. That is what we will do. It will be clear in a moment why we are doing this. So, I can write psi f h interaction psi I as minus E h cross square over V q square integral del square, well, del is a vector operator. Sometimes I will put that vector sign, sometimes I will not put it, but you just see that that is actually del is a gradient, which is basically a vector operator. So, when we say del square, you understand that it is del dot del e power I q dot x over h cross times phi x. So, this del square acts only on this phi x d 3 x. Now, we will consider Green's theorem. Which says that if you have two functions, scalar functions u and v, then u del square v minus v del square u d 3x over a volume V is equal to surface integral of u some surface integral which will actually vanish if u and v are zeros at the boundaries. Okay, so let me say that again. So, Green's theorem says that if you have two scalar functions which are functions of coordinates x, then integral over the volume u del square v minus v del square u d 3 x is equal to 0 if u and v vanishes at the boundaries, bounding surface. Any volume is bounded by a surface, closed surface, and if u and v vanish in the surface, this right hand side of this is equal to 0. In our case, we have a situation where we consider everything happening in a large volume. For example, when you consider the scattering experiment, everything happens in a small bounded, in a small volume, and then outside that all of these activities can be thought of to be 0. The electrons, the beams, electron beams, the electron itself is present only in a finite volume, and similarly the target, and the detection is also done in that volume. So, in that case, if you take a sufficiently large volume, that is what we have been considering when we set V as our normalization in psi and earlier also. We had that in mind, that we are confining everything in a large volume V, okay? And outside that none of this, or there is no probability for a particle, electron or the target particle to exist either initially or finally. And this is valid for any u and v. The only condition is that there should be 0 vanishing at the bounding surface. So, look at the earlier expression for the probability amplitude. We have an integral del square exponential I q dot x over h cross. So, u can be thought of as exponential I q dot x over h cross, and v can be thought of as phi x. So, I can actually swap this u and v and write it as psi f h interaction psi I is equal to minus E square h cross square V q square integral exponential I q dot x over h cross, now u del square acting on phi d 3 x. This is as per Green's theorem. We are talking about electrostatics, and therefore, del square phi should be equal to minus rho over the charge density over epsilon 0, where rho, this rho is different from the rho we considered earlier. Rho is the charge density, electrostatic charge density. For example, for a point particle, this rho would be a delta function. So, then we can write psi f E h I n t psi I equal to minus sign in del square f cancels with an already existing minus sign, E over V h cross over square over q square integral del square phi is rho x e power I q dot x over h cross d3x. Now, this is the electrostatic potential, the phi is the electrostatic potential seen by the electron, and that is due to the presence of the nucleus in our present case. And we know that the nucleus has a charge Z e. So, rho of x is equal to Z e. Question is whether it is a point particle, which means it exists only at a particular point x equal to some x 0. In that case, the density is the total charge times the delta function. Otherwise, we can actually associate a distribution function phi x with this, which will tell you how the charge is distributed in space. Since total charge is Z e, f of x d3x over the whole volume is equal to 1, which is the normalization that we have. So, now look at the earlier integral in the probability amplitude. That can be written as E over V h cross over q square Z e integral f of x e power I q dot x over h cross d3x. This integral f of x e power I q x over h cross d3x is the Fourier transform of f x. And since x is integrated out, it is a function only of q. So, we will write it as psi f h I n t psi I equal to z e square h cross square over v. Of course, I missed an epsilon 0 in all this. So, rho over epsilon 0 was there. V epsilon 0 q square integral over this thing I will write as f q, the Fourier transform of this. And this f q is called the form factor of, or basically this is the Fourier transform of small f x, which is the spatial distribution of the charge density. And look at the form factor. We know the Fourier transform of delta function. As I said, if it is a point particle, the charge density is z e times delta function. In that case, f x is basically delta function, and Fourier transform of delta function is 1 integral delta x d3x is equal to integral delta x e power I q dot x d3x is equal to 1. So, that is saying that in that case f q is equal to 1, and therefore, probability density comes down to z e square over h cross z e square h cross square over v epsilon 0 q square, and the corresponding cross section d sigma over d omega is equal to v square over e square 2 pi square h cross C4, we had a factor of 4 pi which we have. Then the probability amplitude square z square E4 h cross over power 4 divided by epsilon 0 square v square q square f q square. V factor cancels out, h power 4 cancels out, there are all these factors which will cancel out. So, you essentially have this as e square over c power 4 2 pi square c 4 4 pi epsilon 0 square q square and z square E 4, okay, f q square. And if it is a point particle, if we consider it as a point particle, then you will have f q equal to 1 and the rest of it will give you the Rutherford scattering expression once you identify or rewrite the q in terms of the scattering angle. Remember, q is p minus q, this thing. So, we can in fact get that from, there is this initial momentum and final momentum, and q is p minus p prime. So, it is p minus p prime, and from the relation between these we will get q square actually equal to p, if we consider the elastic scattering, that the magnitude of p remains the same, then you can take, it will get that 1 over sine power 4 theta by 2 from q square. I will leave that part to you to work out, but essentially we will get the Rutherford scattering amplitude scattering cross section expression if we put f q equal to 1. So, what is f q? As we said, it is evidently, it is very clear that f q is basically the information about the charge distribution. Now, we had to do an experiment, we do not know what that is, say a priori, and then we do a scattering experiment. D sigma over d omega can be experimentally determined, and we will have to fit this experimental result for different momenta etc., to the right hand side of this expression and find out what is f q, and that will give you information about what is the charge distribution. And if there are clumps, this clustering there, then we will get information about that clustering of charge distribution inside the nucleus. So, that is the idea. So, we will get to that in the next discussion.